Thank you for coming. As you hear this morning, my name is Aleksandar Sedmak, and once again I am chairman and in a way, creator of this session. Next Wednesday, on 3rd of December, Jim Rice will be 85. And I thought it is a good idea to celebrate ahead of time, but we didn't have any choice in that respect. And of course, probably unnecessary, but maybe to explain why is Jim Rice so important. In my view, he is the biggest name ever in fracture mechanics. When I was young and later on, whenever I learned about something new, starting with J-integral, singular finite elements, micromechanical modeling, fatigue, elastic plastic, including some specific cases, viscoplasticity, interfaces, and maybe even more. In all of these fields, it was always Jim Rice who was either the first or contributed in a very, very significant way. Unfortunately, he cannot join us today even online. He has some problems with electricity and heating at his home. So he's probably at this moment trembling in his basement and cannot really join us. But in any case, all the best for Jim Rice and long live Jim. Concept for this session was that, is that I will present direct measurement of J-integral. So to revive once again this milestone of fracture mechanics development. Then Zhang will present micromechanical modeling, complete Gurson model. And for this lecture, I have to offer additional explanation. Here by his side sits Marica. Please stand up, and daughter Sandra. Marica is the widow of Marko Rakin. My good friend who passed away 3 years ago, or 2 years ago, 2 years ago, summer. And he was expert in micromechanical modeling. His doctoral thesis was in micromechanical modeling. And Zhiliang Zhang dedicated his lecture to Marko Rakin. Thank you. Then Queen Zhengfang from Wuhan Institute in China will present a lecture on viscoplasticity and damage evaluation for reliable engineering, which will resemble, in a way, elastic plastic and viscoplastic fields and fracture mechanics parameters. Finally, Ružica Nikolić, one of Jim Rice's doctoral candidates who completed her thesis with Jim. She will tell us online, she's in Slovakia, about Jim, some anecdotes and from private life, because they became friends later on. There was a plan also when I invited Leslie Bank Sills, but she also has some troubles with online and health, so she couldn't join us. She was supposed to talk about interfaces or singular elements. In each case, she is an expert. So as the chairman of this session, let me now give the floor to the first presenter, and that's me. Yes, it's here. Direct measurement of J integral is one aspect of J integral which is not really well known. I will explain why it is, to me, so important and interesting, and it is a kind of mystery for me that it was not more used in last couple of decades, because this is actually a old story, nothing new. So first, to remind you about the J integral, from one of its aspects, which is common for fracture mechanics parameters. From one side, we treat them as a material property, and this is represented here by JR curve. You can see it here. And this is to be measured. And from the other point of view, we can interpret J integral as crack driving force. And these are crack driving forces for different levels of stress, of loading. And we calculate that. Could be measured, but it's tricky. Basically speaking, crack driving forces are calculated, and material property J curve are measured. Now, direct measurement of J integral is a kind of breaking this barrier, and maybe a different interpretation of this parameter on its own. It is the original paper that we have used from time to time here in Serbia and also in USA, while we had a large USA ex-Yugoslavia project back in 1982 to 1990. Cooperation with one of the key men in this project was Dave Reed, who is here mentioned. And just to remind you, J integral is line integral independent of the path. It's all about energy. It is strain energy. It is some stress tensors, some displacement involved. When we develop it into components, we can write strain energy as shown here. And then for some specific problems, we can reduce it to just to strains. Now let me say more details about that. You can see this figure here. This is a simple tension of a panel specimen, let's call it. It's not exactly specimen, but sorry, it's plate or panel. We use different terms in tension, and there is a crack here, and there is a path all over this crack, but so-called outer path. Outer because you can see it goes from A on the outer surface, then it crosses the panel all the way back through outer surface, once again crossing the panel and going back here as the outer contour. One of the assumptions in this story is that behavior of material is elastic, ideally plastic, although corrections are possible if there is some kind of strengthening. So not to going into details, that's not the purpose of this presentation, but just briefly, you can see that we can now calculate strain energy, tensile forces along different segments, and then we also should somehow estimate this component, which is not as simple as the other ones, but that can be done if we can also, we have to actually measure crack mouth opening displacement. If we can do that, we can separate components along paths, and we can finally calculate and or measure J integral. That's now interesting feature of this story. This is how actually one of the measurements was done. There are all these strain gauges. This is quite old, more than 40 years. It was done in National Institute of Standards and Technology in Boulder. Dave Reed was doing it together with Blagoy Petrovsky, who was then visiting scientist there. You can see that crack was positioned in a welded joint. Once again, not very important, but it has some consequences. And, oh, sorry, just for a second to go back. At the same time, standard 3-point bending specimen is shown here for a comparison. I'll explain soon. More details about the crack and more details about the path. Misak, help. What happened? Oh, okay, just another click. Okay, thank you. These M's are actually strain gauges, and there is a CMOD, oh my God, CMOD gauge measurement device here, and that's all we need. So just memorize that all we need are strains along the outer path plus CMOD measurement device to measure it, and strain gauges along the other outer part. Knowing all that, we can get J integral by direct measurement because we can use those simplified expressions that I showed. And then it is interesting to compare JR curves obtained in this way, and I'm showing them as they are measured by panel tension short or other crack. They are actually wrongly marked here. Oh, no. Surface crack. No. Doesn't matter really. Two different crack lengths and two different J curves positioned differently. And then just to compare it with 3-point bending, you can see that crack resistance is higher for panel, tensile panel specimens or tensile panels. This is obvious, reason is obvious. 3-point bending is more harsh loading than tension. But on the other hand side, we of course we like to have conservative approach. This is why we use 3-point bending. But from the other hand side, for example, for pressure vessels, we also like to have to know a real behavior of material or structure. That is the question. We'll come to that. So just another figure of these JR curves. And now they are positioned in a plot with the crack driving force. And now I come to the most interesting part of this story. In ex-Yugoslavia, there were on 2 occasions very interesting experiments made on pressure vessels. You can see here that there is a part of this pressure vessel which was cut out and then welded back. In the meantime, complete instrumentation for measuring of strains was installed. So that was kind of a unique experiment that enabled us to measure J integral on a pressure vessel. Without this piece of cutout piece, you cannot approach the inner side, and we need both outer and inner side. Now, a couple of interesting results which show strain distribution on the side of the crack and on the opposite side. And you should notice a difference in these strain distributions, because that difference is actually, as I will show you soon in a simpler example, measure of J integral. Simplified, even more simplified measure of J integral. So let me explain what I mean. Now, this is probably the simplest possible that one can get. Clamped plate, no rotation, no bending, just tension, and distribution of strains along the cracked side and along uncracked side. So for the cracked side, this one, it goes to zero when there is a crack, no deformation. When distance from the crack is long enough, they are the same. In other words, difference between them, this shaded surface, is actually J integral in its simplest form. So, since this way of loading and this sketch is practically the same as in a cylindrical pressure vessel, theoretically speaking, we can measure J integral just by measuring and estimating this point here and approximating this shaded area. There are some obstacles, of course, and complications which can be solved. My main message is that there is an option to measure directly J integral on a structure. And in this sense, it is both material property and structure property. It is actually exactly what we need to estimate or evaluate critical state of a structure, pressure vessel in this case. Well, it is a bit complicated, of course, but you can't get better than that to precisely evaluate critical state of the pressure vessel. So let me conclude. Actually, I put all what I already said in these conclusions, but I want to emphasize this in red color. So whatever I said now, it is nothing else but the variation of the fundamental brilliant work of Jim Rice back in 1968, because he didn't just introduce J integral then, but he also correlated J integral in this paper with crack driving force and with material resistance. And also he made a correlation with crack tip opening displacement. People tend to forget how complete that paper actually was. And as I already said, that is the most important paper in fracture mechanics history, in my view, and so is Jim Rice. Thank you. Now I would ask Professor Zhiliang Zhang from NTNU, Norway, to present micromechanical modeling as dedicated to Marko Rakin. We'll probably need a couple of minutes for technical adjustments. And in the meantime, also younger daughter of Marko Rakin is with us. Okay, where would you like to be here? Sad vidite šta možemo da sa njim. On ima Zoom.
We can't hear anything.
Yes, please.
Is the mic turned on? I can't hear anything.
Yeah, Alexander, thank you very much for the invitation. I was thinking when I came here, I did not intend to make any talk. I was thinking I could sit here, sit at the conference and relax and enjoy the fantastic talks. But I got an email from Alexander and he said, would you like to give a talk for two purposes? One is dedicated to Professor Jim Wright's 85th birthday, and another one is dedicated to a good colleague, Marko Rakin. I said yes, immediately. So I'm very happy to come here to especially to give a talk in this special event station, as I said, dedicated to Professor Jim Rice and to Dr. Marko Rakin. I was I had my first sabbatical in 2000 and 2001 at Harvard in John Hutchinson and Mr. Vanessa. I did not have collaboration with Professor Jim Rice, but I followed his one of his courses, and I also talked to him a few times in his office. I think, as Alexander said, I think Jim Rice is not only a giant in fraction mechanics, he's a giant in mechanics in general. So I think I got a lot of inspiration from him until today. And Marko Rakin, I think it was when I was in the States, first time on my sabbatical in Harvard, I got contact with Marko, and he wrote to me that he was interested in having a copy of my complete Gurson UMAT code. And at that time I already distributed freely to the world, and I was very happy to give a copy to Marko Rakin. And it turned out that Marko was one of the few colleagues who really understand the essence of complete Gurson model. And I think he was one of the promoters of complete Gurson model. I was very happy for that. And today I was very happy to see Marko's family. Okay, that was the introduction. Today I will talk some insights into the micromechanical modeling of ductile fracture. This is my overview. So first, I will talk micromechanical modeling of ductile fracture. And especially I will mention the cell model analysis, which provide the ground truth data for benchmarking and for calibrating of analytical equations. Then I will mention one of the most popular models in ductile fracture, the GTN model. I think most of you have heard about GTN model. And I will mention two weaknesses of GTN model. First is incompleteness. Second one is non-uniqueness. These are related together. And then I will briefly bring you to the complete Gurson model, which I named it maybe more than 30 years ago. And then I will talk about the CSM, complete Gurson model strategy for parameter identification. I mean, that's to identify, to have a model is one thing, to have parameter is another thing. So we have to have a good strategy to identify the parameters. And then I will talk one unexplored application about of the complete Gaussian model. Then some takeaways. Okay, so how do you know how we teach fracture mechanics today? I mean, when we teach fracture mechanics, first we tell the students that there is a corrective stress field, right? This field was controlled by one parameter, either J integral, Alexandar talked about, that's from Jim Rice, and I, or controlled by CTUV. Okay, so several weeks later, we'll tell the students that that's not true indeed. I mean, corrective stress field is not controlled by one single parameter. It's controlled by maybe another parameter. We will have T stress or Q stress. So here we will have what I have plotted here that I mean corrective stress fields may be controlled by TZ. Professor Guan has a fantastic talk today about the TZ constraint parameter. But in general, what we are telling that the fracture toughness is not a constant. It depends on the corrective. I mean, fracture toughness depends on the corrective constraint. Okay, transferability is a challenge. We cannot do the transfer. We cannot transfer from one geometry to another one. That's a challenge. And then what we can see, what we can demonstrate is that micromechanical modeling could offer alternative transferability. That's my starting point. I will end the transferability of my talk. Okay? Then what is micromechanical modeling? Micromechanical modeling is a kind of physics-based approach used to predict the macroscopic properties based on local properties and microstructural features. So if you look at the specimen on the left, and we could easily identify a kind of unit cell model. Here I have a unit cell model in the center, and I have four keywords. First is there should be a periodicity. That means we can repeat this unit cell model. And at the bottom, there is an approximation. I mean, it's always approximate of the microstructure. I mean, microstructure is always more complicated than the model itself. And then with the unit cell, we can study the morphology. That includes the size, shape, distribution of these faces, and morphology and local properties on the right, on the macroscopic behavior. So we have on the right hand side we have ground truth data. That is a kind of data we can use for benchmarking analytic results. For example, benchmarking the Gurson model and the GTN model. We can use use AI to identify the critical microstructure which can realize the optimal performance. So this is going to be the optimal microstructure, and so these things we can do with micromechanical modeling. Okay, let's look at ductile fracture. That's my talk. Ductile fracture is kind of a field which is massive. I mean, everyone has heard about this. I mean, it's there are a lot of studies already have been carried out. So ductile fracture mechanism, we know it's if you look at the fracture surface, there are a lot of dimples. So we have three stages of ductile fracture mechanism. We have void nucleation, and that's from the particles through particle fracture or particle debonding to the matrix. And we have, I mean, this nucleation is could be stress or strain controlled. We could have plasticity induced vacancies that could nucleate void. This is very exciting for the hydrogen embrittlement, which we are working now. And then once the voids have been nucleated, then these voids have under the plastic deformation and stress tractility, hydrostatic stress, these voids will grow. So, I mean, then at certain stages, the void glow will be stopped. So we will have void failure. That's also called a coalescence or plastic localization by void making or, I mean, sheeting. Here we have two types of loading. One is tensile, another shear. And in this talk, we will focus on tensile loading. My question is, can you guess, is void coalescence stress controlled or strain controlled? This is, I will ask you later. So let's talk about cell model. So for ductile fracture, we can easily identify a two-phase cell model. I mean, one phase is a matrix material. That's easily we can understand. Another phase is empty, nothing. So it's we have a hole inside. This is a very typical phase cell model for the ductile fracture. If we make cell model analysis, that means we can carry out numerical analysis of this cell model. What we need to have input. We will have the matrix property. That's sigma 0, that's yield stress and hardening, right? Sigma 0 and n, these are the matrix material property. Okay? Then we can have a kind of F0, that's initial for the volume fraction. That's the only input we need. And then we apply a load to this cell model. Then we will have output here. On the right-hand side is output. We will have deformation and fracture. That means this cell model can automatically, in fact, we can use the word autonomously, controls deformation and fracture. Deformation, that's a homogeneous plastic flow, and the fracture, that's a localized plastic flow. So that means cell model can reveal both the deformation and the fracture. That's important. And that means it's complete. Cell model is complete. That means it can reveal both deformation and fracture. Okay, this is completeness. Then cell model is also unique. If we try different void volume fraction, on the left you have yellow, and you have red and purple and green. So different F0, then you will get different ductility, right? So this is unique. There is a one-to-one relation between the void, initial void volume fraction and ductility. That's important. So for cell model analysis, we have both the completeness and the uniqueness. What about the model, analytical model? Let's take all these models available. So we have everyone knows about von Mises model. I mean, sitting here. Von Mises model could be regarded as a kind of micromechanical model as well. So let's start with the von Mises model. Von Mises model is a kind of yield function, right? There is no inherent failure criteria. You can use the von Mises model to analyze the problem, but it can yield. It can not fail. That's important message. Then let's look at the Rice-Tracy model. I mean, here, Professor Rice again. It's a very famous model. And if you think about, we have infinitely large plastic domain. Inside, we have a very small void. And under the plastic deformation and hydrostatic stress applied, then we will have void expansion. So Rice-Tracy model can calculate the R dot over R. This is interesting. I mean, but there is no inherent failure criteria. That means you can probably use a kind of critical value for this expansion, but you cannot predict the failure. Then let's go to Gurson model. Gurson shrink the infinite large media to a finite media. Okay, then you have a void volume fraction instead of void radius. So you have V cell over a V and void over V cell. So you have F, and you have a yield function as well. And this yield function is interesting. Gerson's yield function considers the effect of void volume fraction. That means if you have a large void volume fraction, it's easy to yield. If you have a lower void volume fraction, it's difficult to yield. And it's a kind of you can Gerson model can calculate the void growth. So it's a yield function itself, but it can consider the void growth model. But unfortunately, there is no inherent criteria as well. So then let's go back to the most famous model, GTN model. GTN model, I mean, after the work of Tverbgard and Needleman, Gaussian model becomes quite capable. GTN becomes quite capable model. It can consider the void nucleation. So we could have a cluster nucleation, we could have a continuous nucleation, we could have a statistical nucleation. It could be stress controlled, it could be strain controlled. Okay? And then we could have void growth. Void growth is the Gaussian model, so it's already there. Then I mean, GTN model could consider void failure. But I mean, it provide a framework for considering void failure. But there is it needs FC. It needs the critical void volume fraction. There is no inherent criteria. Maybe it's confusing, but let me explain a little bit more. So FC indeed it was taken. It was assumed by Tverbgard as a constant, Tverbgard-Needleman. But it turned out that it's not constant. I used the Copernic-Needleman data and I found that I mean the FC depends on the stress characteristic, depends on the initial void volume fraction. That means it's not correct to assume FC is a constant. So my conclusion is that GTN can model void nucleation, can predict the void growth, but unable to predict the void failure. So it's not complete. There is incompleteness problem. And because of this incompleteness problem, then there is another problem called the non-uniqueness problem. For a natural specimen, you can find infinitely number of sets from F0 to FC sets, which give identical or almost identical curve. So in fact, you can have a kind of equation. FC will be equal to a function of F0. That means the the problem is that different initial conditions can lead to same ductility. That's a problem. So because of this weakness of the GTN, I think that was around 30 years ago. I was inspired by Thomason's work. I I tried to incorporate Thomason's Gurson model into Gurson. So because ductile fracture is a complete ductile fracture model should include both the void growth, void nucleation growth, and coalescence. So GTN is not complete because it cannot predict the void failure. So in GTN, because coalescence is simulated by an arbitrary and negotiable FC. So by incorporating GTN with the physical coalescence model, then we get the so-called complete Gaussian model. Complete Gaussian model is not only one, it could be many. So here is a kind of illustration. So we have x-axis is equivalent plastic strength, y-axis is maximum principal strength. So black curve is the kind of GTN curve. And then we add one additional mode, deformation mode. That's called localized deformation mode. This localized deformation mode is not working until these two curves cross each other. So in the beginning, it's not possible to have localized deformation until one void are large enough. Then you could have localized deformation. Okay. And then we can have analysis of the parameters involved in CGM. So CGM, we have yield stress, sigma zero, Young's modulus, that's given, and Poisson ratio, that's given, and plastic strength, that's also given. Then we have Q1, Q2, and Q3, that's 12 kinds of parameter. In principle, this can be fitted very nicely as a function of N hardening. So I mean, with machine learning technique, we can have a perfect fitting of this. And then we have FC, that's not a constant. FC determined automatically. Then FF, can be determined, set to zero point 0.2. I mean, Benzaga and Leblanc has a lot of data on that. Then we have FQ, that can be determined. So the only parameter left without determination, that's the nucleation parameter. So we can use single specimen strategy or multi-specimen strategy to determine to fit the nucleation parameter. So because nucleation parameter is the only parameter which needs to be determined, it links to the material failure one-to-one by one-to-one relation. So here are the strategies to fit. If we use one single specimen, then we can, for example, make different calculations with the void volume fraction, initial void volume fraction. Then we one fits the experiment very well. Then if we use multi-specimen strategy, then we can fit the ductility. So these are the if so we can use different integration model. If the cluster model is not working, then we can use the continuous model. And if the continuous model is not working, then we can use the statistical model. So my advice is that try simple model first. And then this is my last one of the last slides. Transferability, I mean, we should have a resistance curve. I mean, we could have JR from fracture mechanics specimen. and to the component. But in fact, due to the constraint, this is not working. So this is not working. Then we can have transferability by void nucleation parameter and plus a kind of length parameter, characteristic length parameter, LC. That's the way of transfer from small specimen in the laboratory and to the large components in service condition. So we have to have both low stress gradient specimen and high stress gradient specimen. Okay. Another unexplored application is, I mean, we know that we have a high strength steel, low strength steel, medium strength steel. But have you heard about high strength steel, but high ductility steel, low ductility steel? So you have never heard about this, but it's very much needed. So we have a ductility is horizontal, strength is vertical. So we could use the nucleation parameter to classify material, classify the steel by this way. So this we could have low ductility steel and high ductility steel. So this is possible. Okay, this is my last slide. Void nucleation is the root cause, is the thing of, is the original thing of ductile fracture. Void coalescence is stress control. I mean, that may be surprising to many. I mean, GTN is not complete, has a non-uniqueness problem. CGM, complete Gurson model, links the ductile fracture to FN. FN, that's nucleation parameter. And F0 is not the same as volume fraction of particles. I mean, we have Franklin's equation for calculating the volume fraction of particles, but I think it's not the same. And Fn, the nucleation parameter, can be inversely determined. Fn can be maybe used for classification of ductility, and maybe can be used for unifying brittle and ductile fracture. That's what we are working. And my last message is the fewer the parameter, the better. Not obvious. Yes, thank you.
Thank you, Qian. A small appreciation from our side. Please, this is for you, Nikola Tesla, my inventions. Thank you very much for this comprehensive and very, very nice talk on Zhiliang Zhang model, which is named complete Gurson model out of modesty of our guest. Now, Professor Zhengfang
Qian.
Oh, sorry. Sorry. Yes. Well, it's difficult. Yes. Thank you. He will talk about viscoplasticity and damage evaluation.
Not this one?
Reliability engineering.
That one? Just share screen.
We have to share the screen. Okay. Can you see my one? Share the screen first. Open my file. Can you open my file now?
Yes, of course.
Okay.
Just a second.
You go ahead.
Where is your file?
Should you
Parallel session 1, parallel session 2.
No. I still inside the USB and
Okay.
here. Let me do here. Okay. And go to the first page. Okay. Hello, everyone. So a little bit late now, and I'm very glad and give me a chance I can present here now. I have 40 PPTs. I can go 20 minutes. Okay, maybe less. And later on we can do picture work, okay? And my topic is viscoplasticity with damage evolution for reliability engineering. My last name in Chinese is money, in American called dollar, but nobody can explain them. Simply call me ZQ. That will be nice and easy. First one, I will talk about what is really considered equations. There's many confusing and in the area, and people really don't understand what is the considered equations. Let me put it this way. Left side is stress, right side is strain. You can jump by stress to the strain, or you can put strain up to the stress, okay? Traditionally, people think that that's the relationship between the strain and the stress. I will say it's not that simple. And that just also is not a curve fitting, okay? From mechanics point of view, consider equation is multidimensional tensor differential equations. It's quite complicated. The first point of view. Second one, like the professor just said, if you don't have the failure criteria or the fracture criteria, you only get stress and strain, you get nothing else. You can't predict how the structure going to fail. I will show you, we can show you exactly the failure processing, okay, you put on. And another way, people also don't really do time and physical scales. Scales very important, depending on which the engineering problem or scientific problem you're going to attack. So put all those together, that becomes powerful considerable equations. Then you can do the computational and the simulation, and they can show you, I can show you real case study, you see how powerful it is. And by the way, and let's see the classifications, okay. Elasticity, only one name is hook, and the super elasticity is nonlinear, recoverable. There's already come out names. I'm not going to point all of them, money, revenue, whatever. Now we come to the physical elasticity. And up to the plasticity used to be have two. One is called a rate independent. Another is called a rate dependent. Rate dependent is equal to physical plasticity. This includes temperature, rate, time, almost everything. So physical plasticity will include the plasticity, elasticity. I did one from the physical elasticity to physical plasticity. We can unify all them together in one university or in one universal considerable equations. Oh, later on. I did this about 20 or 30 years ago during my PhD thesis. That all comes out generalized now. We call that, he introduced the internal variable theory in the 1971. That's my start point for my PhD. Later on, I will show you exactly how that goes to. Then I find these are the Harvard and going to grading the theory. Actually, from quantum mechanics point of view, there is so many grading theory. So I don't think it's new. And then you put on the micro, nano, right? Atomic, then quantum to multi-scale. The presentation, the PPT will show you how to do the multiple calculation of multiple physics. And then I really like to say, any equations, we do need checkpoints, okay? Not just curve fitting. You have to put some critical say, how good that is, how bad that is. For instance, all the check for the cyclic loading is a very good one, special like this. This is called a cyclic hardening, cyclic softening. Actually, this is kind of damage processing. That's for the metal. If you look at the polymer, okay, that's more complicated. This is the polymer cyclic loading and unloading. But this is only one dimensional. And really, you're going to check later on, I will show you, at least it should be two-dimensional. Otherwise, you still can't say that's good or not. During my PhD thesis, actually, it's one by Japanese scientists and India did, is if you do creep, then plasticity, then creep. They also done another analysis to the plasticity, creep, and the plasticity. They check more than 20 considered models. None of them is good. That's my start point, how I can develop a considerable equations can cover all of this. I spent 1 year, very hard time to get the solution. Here comes, and why I start point actually is from Jim Rice. I didn't have the chance to worship him. Let's look at his first 1971 paper.
Now you're going.
This is called inelastic considerable relations for solids. Okay, an internal variable theory and its application to metal plasticity. Let's start with the slip system. Okay, then this tensor, how to decomposition. This is defined. One is deformation, another is rotation. And then, that system also, they started with rate dependent. Actually, this is kind of physical. And so this start point one is from the slip system. Later on, we have a new PhD student. He repeated it again. Okay, this is called texture. And then you can do the anisotropic plasticity. But I would say Max Planck did a very good job for this, okay? And they published the whole program is free on their website. I get very impressed of that. I think someday I will open my old program to the website. Okay, when I attack this problem, my internal variable theory come to another level. I call it dislocation theory and dislocation dynamics. And this one, I built a model called a glide plus climb deformation dislocation model. Glide is plasticity slip. Climb is creep. The dislocation can go from one plane to another plane, driven by the creep deformation or the creep, whatever damage or later on. Actually, this is the model. When I did this, and I first visited to the US with the EC apprentice. This guy is a very good guy, but also very elegant. Actually, gradient theory should be credited to the EC apprentice. Harvard actually is followed him, and but apprentice have some defect, I would say, in his tensor equation, and but that doesn't mean his physical model is wrong. For instance, we discussed the hard and soft two-phase dislocation model, and that time he back to the Greece. He asked me back to the China. I said no. My wife said no, not me. Okay. There is one Chinese, very senior, and they call it Zhiliang. Actually, he's the one followed apprentice to the gradient theory. And he left the academia, otherwise will be the graded to this theory. Okay. Then I back to the one just to the professor now. I attack the same question. The Gurson model, what I will say, I get analytical solution for the voids, and also I get a criteria use inclusion. I mean, that's I have this book, basic inclusion, tensor analysis, then I get all the analytical solution. Driving force is for the plastic deformation or inelastic deformation. But the effect is they will damage the Young's modulus. That's what I did. And using inclusion, I get an analytical solution. All that comes, I also get a criterion, exactly 50%. Okay, but this maybe not the analytical solution. 50% Young's modulus will go to 0. I use this one to do the crack automatically generated. You will see that. Okay, let's talk about the reliability engineering. We use the constitutive equations. This is my own opinion, okay? Not means, I mean fatigue, creep, relaxing, fraction, damage, corrosion is something else, okay? Creep, fatigue, creep plus ratcheting, buckling is something else too. Most of those can be solved with constitutive equations because they come from loading condition. They come from environment effects. They come from defects, right? If you put all those inside correctly in the constitutive equations and the computation, they can tell you what's going to happen. How the reliability can be predicted. We can do predictive reliability. That means we really can predict and not guess. Okay, since I'm the presenter, I want to do a little bit of brief history. Okay, it's not full. Most of people get the Norton law. This is one-dimensional high power law. In my opinion, this is not a constitutive equation, just a curve fitting. Okay, second one is for Pazina, actually from Europe. You see, I remember he was a Polish Academy member. And he has a model called overstress. Okay. Then I come to America and meet Krimpo. He's extended this model. When I meet Krimpo is already 30 years old. His hand is shaking. That time I'm still wondering, he's still the full professor in the university. Then later on I learned American have the permanent job for the professor. I think that's very nice things. Okay, then the French, Chaboche. Chaboche model actually part of, I would say, no, I come on the one good name is called Valanis. Okay, my PhD advisor is Zhengfang, and he followed Valanis, got a PhD degree in his age about 48 years old. And he comes, I'm his first PhD student. And he asked me to do ratcheting. I said, ratcheting is just part of the constitutive equations. So I want to give more to the distribution theory and build it up for this. That's what I did. And one important thing, the contribution is very good. He called his yield his plastic model or the physical plastic model, there is no yield surface. Okay, this is quite confusing, right? I will talk to you later on. Many people ask my advice about this question. He didn't answer. Finally, I figured out why. I can talk to here now. It's not no yield surface. Instead, they have infinity yield surface. Okay, infinity yield surface. So that's what my model actually inherited this idea. Okay, actually I developed this model, asked Dr. Liu, okay? He said right now, it's called a Qian new model, okay? Actually I did this model about 10 years. Started from my PhD. I even used this model to analytical solution for the residual stress that published in Chinese, okay, in 1989. That time I was a PhD student. And then I do the first publication actually in the American, NASA called this meeting. And chair was Dr. Fried, and from NASA Center. And he invited me to give a presentation. And later on, we used this model to a kind of special material called solid alloys. You open the computer or your cell phone, there's lots of solder joints. If something failed, very likely it's solder joints, okay? And so then we use this one for the solder joints. Later I'll show you. It's a very good material to check consider models, okay? And then when I went to the Motorola corporate for my job, that time, I don't have enough data to verify my model. And then we found there's tons of failure data and verified my model, but we still publish this paper 5 years later. Actually, I finished the job in 2003, then let me publish in 2008, okay? This is a brief history. Let me go a little bit quickly. Later on now. I introduced the 4 internal variables for our whole. This is called unified physical constitutive equations. Okay. The first one we call back stress is tensor. This actually means plasticity. Second one is called drag stress. This means physical. And the third one, yield stress, the traditional, right? The fourth one, void Pearson model is damage invariable. Only trick is how do you get that differential equation? Okay, I have almost this is analytical solution did it. Let's show you my PhD work. This is for the stainless steel cooking the 600 degrees C. Like I said, for the tension and the creep, it's not a big deal, but the big deal is the creep is a very long time, very slow rate. And the tension is a high rate. The strain rate almost close 11 order. And in my time, I didn't find any constitutive model can fit 11 orders. I did it. And the second one is more difficult is this testing. Oh, did I show it? Maybe later on I show you. The creep to plasticity and to creep. Now plasticity to creep and to, that is very challenging too, okay? And then, like I said, any constitutive model, if you can't do the algorithm, you put on the paper, nobody can use it, okay? Then I started to the implementation. That time I work in the Wednesday University, okay? I spent the lab for 3 months, day and night, to check out where it was wrong. Except yourself, nobody can tell you where it's wrong, especially about the program. Okay, this algorithm called the return mapping. Yeah, this is developed by the Stanford University, this algorithm. And then you have to do this for the first guess, initial solution was elastic, and then try to come back to correct it to the right solution. And then you have to develop all the back stress, jack stress, yield stress, damage. You have to all update them for the integration. And the important thing is you have to make sure that converging, okay? Here is, most of people don't understand this. You see this? When you do the loading and unloading, the modulus will jump 1, 2, 3, 4, 5 orders. It's called the stiff equations. Most of commercial finite element code failed by this. You just see directly. I have a guy when I was Stanford. His advisor is the academician of American Academy. And he come from Tsinghua University, the #1 in China. He asked me, how do you do the cutback for this? I said, my constitutive model and the computation go automatically. He looked at me. You never believe. Anyway, that's why I said only trick is I have infinite yield surface. Okay, that's how it did. They have a specially mathematical structure. Okay, I come back because we should do copyright, right? So I did copyright. And later on, if really I will release this copyright to everybody. Okay, let's check it. Like I said, after this point, we already started software. We call that damage evolution, right? This is damage evolution, the cosmos. And then we can see all the creeps. All the creeps. Here comes one very important. The solid material, it's especially Antarctica place, melt point only 183 degrees C. Okay. And then in the theory, you have the Kelvin, you do Kelvin for the temperature, you divide them by the melting temperature. If above 0.5, that means creep will be significantly contributed, okay? For instance, for the solid joints, 75 degrees C equal to stainless steel about 1000 degrees. So you see, for the stainless steel, most of them can't support like 100 or 1000 degrees C. Okay, so this is very good even in the room temperature. Then we're going to 0.65. In the room temperature, solid joints in your cell phone, in the computer, they will creep automatically, they're so later going to fail. So that's why computer only use for a couple years, 3 or 4 years, they're going to die automatically. Okay, don't worry about it. So sooner or later, they're going to fail. Okay, then the checkpoint here is when you do the cyclic loading. Look at here. You see all the commercial codes. Here, they must be broken. You're going to check it. Check all those equations, if they're broken or not. They use cutback rules, and they don't, most of the time they will be divergent. This is my model. They go automatically. Okay. Left side is the test, is cyclic loading. Another thing is called ratcheting. My PhD advisor was asking me to do ratcheting. I said, ratcheting just one of that. You see, I proved ratcheting is one of the effects from the constraint model. If you do cyclic loading on the pulse like this, the automatic comes out. You don't need a special constraint model for the ratcheting. Okay. I just studied this now back to the mechanical engineering. That was asking me to do. We have flange, we have screws, we have seal by rubbers. What are we going to do? I show you one now. I just did. Okay, let's see if this video works or not. For instance, when you turn the screw, that will have friction. This is contact problem, also geometrically nonlinear. Later on, we will transfer this to the material nonlinear. You will see who, when they're going to fail, how they creep, what is the cycle. Okay, preloading, after loading, you will see all those like that. And they come out automatically. You don't have the special to look at that. Okay, let me give you a real case study to show how powerful this is. Okay, this was a mock one. That's what I worked on when I was in Metropol. The static. Actually, this is the X file. You will see this. We get tons of solid joints come back failed like this way. Okay, especially there is a failure analysis. Let me show. Failure analysis, all correct. Some is started, some is stopped, some is go slow. When all that goes slow, this joint is going to fail. Okay, part of that, you will see the noise. Sometimes it works, sometimes it doesn't work. Okay, that's because the crack just opened. When the close is okay, open, they will change the resistance. Okay, how we can attack this question? Very interesting. This phone have this push buttons, and we was able to identify this most failed IC. You see, the most used key, send key, function key, and the key. This is most. So let me show you quickly now. We identify these keys pushing cause it failed. Okay, this is a finite element model. Then put my our constitutive model with failure criteria for a Gurson model. Now you will see all the correct points. Start here, and the correct will start here. He's just started. And then later on I can show you even how they propagate it automatically. This is starting for the crack. This is two branches start now. Third one you will see they're connected together. You see, this is crack, come to stop, and started here, then they'll put connection, connected together. So finally, this is simulation. These SEM pictures. I didn't do anything. I didn't cheat, okay? Show exactly how they failed. Then like this, we predict all those processes that could start it, that could stop it, that could be connected, okay? And for this one. This one just for my pleasure, okay? How to verify concept models. Like I said, not if you only do one dimensional, that's not sufficient. At least you have to do two dimensional. What I want to show you, I finished my PhD for 4 years. 3 years, I was building this machine. Okay, that time is the first one made in China. And who said it? This is the Professor Zhiliang. Do you know him? He was the president of Chinese NSA. He was the president and the president of Zhejiang University. He's a very high rank. He's my reviewer for my PhD thesis. He said this is the first one built in China. Okay, it's not me. And the second one I will show you say this sensor. I did it exactly. I designed this, built this, calculated this. At that time, I don't know. We should do pattern. We didn't patent it. Okay. And that one is, I think it's intelligent work because you need to 1 year extended the deformation outside the furnace. Second one, you have to separate the rotation with tension. Then measure them separately and control them. Okay, that's what I did. Then I come to one university that's, you see the small sample fatigue test. We built this one especially for IC chip. There is silicon, there is polymer, there is a compound, there is, you name it. Okay, most of the materials we have inside for all those. So it's very complicated, but that means you have to build powerful equations for them. I just said, okay. Then back to this. It's to finally, I built the equation could predict this correctly. And I even found out why other model couldn't do it and what's the reason. So let me go to a little bit now, how we do multiple scale and the simulation, okay? And I will say physical, actually time is physical, but the physical except time put together, you have a scale. This one I was 10 years ago, I write to the NSF, they didn't find me. Anyway, from quantum atomic to the nano, micro, meso, macro. This is the one. Here, you from deformation, failure, simulation, my team right now, we already combined DFT with MD. Ideally, you put DFT, MD, molecular dynamics, FEM dynamics, even failure, all those together. That will be very powerful and close the scale. And this is another my suggestion. Okay, 2015, 2 years ago, I read this proposal when I come back to China first. I think they're totally blinded, okay, the review. I do the tool integration for the multiple scale simulation. All those tools is out there. How do you integrate and make that work for you? Okay, that's the important. Did I get more time? Sorry, I passed much time and I didn't. Okay, this is the last one now. You see the big boss is here, Professor Tu. He invited me to this university now. That's my team. Then we have 1,200 square meters, build a new powerful lab. And welcome you if you can follow us. Okay, join us. Talk to the professor Tu or me, okay? This is my journal. I just want to show you. I spend 12 cities. I enjoy book reading, okay? And I believe life is a cycle. Important is the process. Doesn't matter. From zero and to zero. So don't be worried about that too much. Okay, thanks.
You. Thank you very much. It was very, very interesting and impressive.
Okay,
We'll handle that, don't worry.
Okay.
And Nikola Tesla.
Introduction. Okay. Well, hello, everybody, whoever had patience to wait for me. Thanks. We are running just about 1 hour late. Not my fault. Anyway, my name is Ružica Nikolić. I am currently employed at University of Žilina in northern Slovakia. Originally, I did my education in Serbia and continued with Jim at Harvard. This presentation is going to be semi-personal, not completely, because it's about Jim, not about me. Only a few introductory remarks. I met Jim first in 1983. I got an IREX grant, exchange between, at that time, Yugoslavia and United States, and I was visiting fellow for a year. Then I applied and got a scholarship for PhD studies. So my first impression and meeting was in his room at Harvard, at Pierce Hall, and he said, "Hi, I'm Jim Rice." And for me, that was a little bit too much, because coming from communist Yugoslavia and educated formally, so it was good day, Mr. Professor, and so forth and so on. But I had to learn to, communicate casually. Renata, his wife, joined a bit later on that meeting, so I met them both at that time. Anyway, I continued calling him Professor Rice the whole time. I was in States for about 6 years. And I managed to finally call him Jim since 2011, when we were in Pasadena for his 70th birthday celebration. Okay, as I said, this is not about me. Just one small excerpts from Jim's CV to tell you who he really is. So born in 1940, and that's what we celebrate this year. College degree in 62, master's degree in 63, PhD in 64, all at Lehigh University. And Professor Hutchinson from Harvard said so, and Jim agreed, that actually they gave him PhD to kick him out from Lehigh. And Jim also said that his master's thesis was better than his PhD. So we had to take his word for that. He knows the best. Why was he making trouble? Because, you know, students at the beginning of each class gets the homework assignment which is due within a week or two. The problem was that Jim, when the class ended within an hour or two, Jim was handing in already finished homeworks. So they were a little bit discouraging for the rest of the students. Anyway, he was teaching, as that is at Harvard curriculum at that time, that professor is teaching what is his specialty at graduate courses. So that would be for Jim at that time, fracture mechanics, later geophysics. And when I came in '83, he was teaching thermodynamics of all the courses. And it was interesting for me. It was new because I was already an assistant professor at home, that students can interrupt during the lecture. So he would patiently answer all the questions, explaining some things 2 or 3 times. But once somebody asked about some equation, for one of the first laws of thermodynamics, and Jim just turned around and sharply said, well, young man, that was in mandatory reading for this class, and continued to lecture again. So, you know, this is an interesting point. He knew exactly how to manage students. Jim's main characteristic, as I think, characteristic is as a genius, so that he can, you know, compact everything in a single sentence. For instance, when we wrote our first article, common article, I wrote text in handwriting on some 19 pages and handed in, and he said, oh, this is very good and very bad. One sentence. Not even complete. And I said, excuse me, can you please elaborate on that? And he said, well, this is very good for you and me because we know what is this all about, and very bad for the rest of the people who will be unfortunate to read this. So, you know, you have to have all this explained from the beginning to the end, what you did, why you did, how you did. Another point is that Jim was always paying attention to all of his students. For me, for instance, when I got scholarship switching from visiting fellow to PhD student, he asked me, because he knew that I won't be able to be alone. I was already married for 3, 4, whatever years. So he asked me what your husband is doing. And I said, well, he's finishing a PhD in automatic control and robotics. And Jim said, oh, perfect. He can come and work with Professor Brockett at Harvard Robotics Lab. So that's how my husband ended up studying and actually lecturing at Harvard. Another thing is Jim was almost every year going for 3 months, 6 months, half a year as to sabbatical to Caltech. So one year he was somewhere in February, he had a plan to leave for Caltech in September for the beginning of the new school year. And he made a plan that for those, I don't know, 6 months from February till September, 5 months, 2 to 7 is 7 months, he decided to write 6 articles. And the problem is he didn't write those 6 articles, he wrote 8. Another point of teaching is that, as you probably all know, Jim is not trying to be very smart in dressing, and it was kind of problem for him, you know, once when he got a honorary degree from one university, one of the universities, he had to put all the gown on, and it was the biggest problem. Well, he had a tie on only for the first lecture in semester. And then that tie was happily hung on a hanger, and he was going to classes dressed casually. As I said, genius. We had a problem for one of the articles. to use complex variables and needed conformal mapping from a parallelogram to a circle. So Jim comes on Monday and said, okay, this is what I did 2 hours on Sunday afternoon, and brought me like something between 2 and 3 pages of equations. Well, I needed 2 or 3 pages from one line to another. And that's not that he just wrote all the main lines. He had all that in his mind. So it took me like 20 pages to go through all the equations. And of course, no mistakes from his side. When he needed some finite element calculations, and at that time, that was late 80s, the newly released finite element program was Abacus. And Jim was not very happy about the official explanations, the official manual. So he sat down, learned all about it, and ended up giving a course at Harvard on Abacus. What else? Yeah, some personal points. Okay, everybody will start laughing now. I had a very special relationship with Renata, Jim's wife. She's Polish, and she does statistics in geophysics, and she's editor-in-chief of the most famous journal in geophysics. Anyway, when I wrote my letter to introduce myself to Jim to accept me for that scholarship, at the beginning I said, well, at the end, about my knowledge of English, you can get impression from this letter. And Renata later told me, when I was already there, that that was almost the point that I was not accepted, because there was some fellow who came and somebody else wrote a letter for him. So when he came to Harvard, he couldn't speak a single word of English. And when she was explaining to him that he can write a letter for his family, and if somebody is flying back home to his homeland and can take that letter, Renata had to fly like a plane to explain to him that, you know, he can write a letter and send it. So don't write, my English is good, you can see from the letter, if you're going to write something to Jim. Another point is that we went for lunches like once a month around with Jim and with Renata or both. And Renata loved a lot in a Greek restaurant, lemon soup. So we would go there sort of often. And you know how Greeks love their neighbors. So, because in Serbia, the homemade coffee, home coffee is called Turkish coffee. So I come to a Greek restaurant and I order a Turkish coffee. I was almost kicked out. The waiter was yelling, this is not Greek. There is no such a thing as Turkish coffee. This is Greek coffee and so forth and so on. So I hope that I didn't bother you too long. One thing is also funny. Jim wrote under quotation mark a book that he cannot read. In the 80s, Russians collected some of his works and translated and printed, published as Jim Rice's book in fracture mechanics in Russian language. So Jim wrote a book that he couldn't read. That would be, I guess, all. Jim was also always behaving calmly, never raising his voice. Once I heard about an event, I was not present, that he was yelling at the dean or head of the department because he was asked to prepare the program for the curriculum in mechanics. And well, studiously doing everything, he did this very nicely and handed into at a meeting. And then there were so many remarks and everything that he finally, you know, went through the roof and said, okay, I lost time from my research and from my teaching and everything to write this program, and you are not satisfied with it. Why the hell did you ask me to do that? Well, they say that it was at the meeting and all the doors were closed, but everybody could hear him. I didn't. That's just, urban legend. So, as I said, Jim is a genius, but as every genius, he has flaws. And there is one thing Jim Rice could never learn. Okay, what? To pronounce my name. When I introduced myself to him, I said, well, my name is Ružica, which is in Serbian language diminutive from rose, Ruža, which means actually my name is like a little rose, and I don't feel like that. And of course, it was laughing, but Jim could never pronounce Ružica. I was Ružica, and that's it. Martin, Renata's son, was explaining to him, Jim, this is like pizza, Ružica. No way. So you see, he's not that perfect. Almost, but 9 and like some 7, 8, 9, 99% of that, but he cannot pronounce my name. And this is, of course, we were always joking about that. Anyway, I was talk to Renata, sent email to Renata today to check whether she will and Jim join us. Unfortunately, they had some emergency at the home with problem with heating, and on East Coast it's very warm at this time of the year, and tomorrow is Thanksgiving, so they have to repair that heating ASAP, otherwise it will be nice, and that's why they couldn't appear at this meeting, which is actually dedicated to Jim. So happy birthday to Jim, and happy Thanksgiving to you and Renata, your family, and God bless you all. Thank you.